In this video, we are going to continue talking about the concepts of Chapter 2. Now we're going to move on to talk about radioactivity and radioisotopes. But first, we are going to review the concept that we learned in the last video that has to do with isotopic notation. We're specifically going to look at problem 2.16 on page 53 in the textbook. And as you can see, the instructions read, determine the number of protons, neutrons, and electrons for each of the following atoms. We can observe that in this table, on the left side, we are given isotopic notations for a different number of elements. Let's first review what kind of information does the isotopic notation give us. I'm going to utilize the first example, and I'm going to label the components of an isotopic notation. So the isotopic notation first gives us the chemical, in other words, the element symbol. And as you can see, this capital H represents the element hydrogen. In the top left corner of this isotopic notation, we have the mass number. And remember that this mass number equals the number of protons plus the number of neutrons. In the bottom left corner, we have now the atomic number for our hydrogen isotope, and the atomic number represents the number of protons. And because we're talking about ground state element, it also equals the number of electrons. So given the following isotopic notation, we can already tell that in this isotope, which its name is hydrogen 2, we have 1 proton and 1 electron because of the atomic number. To get the neutrons, we can actually rearrange this equation in order for us to solve for the neutrons. The neutrons, in essence, are going to equal the mass number minus the number of protons. And remember that the number of protons, in essence, is going to be the atomic number. So if we take the mass number minus the atomic number, that will give us the number of neutrons. So in the case for this isotope of hydrogen, we're going to take the value of 2 minus 1, and that will equal 1. So for this isotope of hydrogen, it has 1 proton, 1 neutron, and 1 electron. Make sure that you practice by completing the information for the other elements that we have in the following problem. Now let's proceed to talk about radioactivity. Radioactivity is also known as radioactive decay, and it is the process by which an unstable atomic nucleus loses energy in the form of radiation. If a particular isotope for an element is able to emit radiation, understand that that is what is known as a radioisotope. And you can see the definition in the third bullet point. As an example here, we have different isotopes for the element carbon. We have carbon-12, carbon-13, carbon-14. So even though carbon has different isotopes, only carbon-14 is radioactive. And understand that this is true of many elements. Even though there's different isotopes, they can have one or more isotopes that have an unstable nucleus. So when this nucleus is radioactive and it is unstable, it's going to emit small particles, and that's what we call radiation. Now, why is it that elements are trying to do this? Well, understand that these unstable nucleus, once this particle is released, is going to create a more stable, a lower energy nucleus. So that's why they are going to undergo these changes. There are many forms of radiation, but for the purposes of this course, you only need to be familiar with 4 of them. The first form of nuclear radiation that you need to be familiar with is alpha particle. An alpha particle is going to be a particle that is released by an unstable nucleus, that it is characterized by having 2 protons and 2 neutrons. So that's why overall the mass number for this particle is going to be 4. Now, the atomic number, since it has 2 protons, is going to be equal to 2, and it has a charge of positive 2. So overall, since this particle is characterized by a mass number of 4 and an atomic number of 2, it is identical to the nucleus of a helium atom. That's why you see that when we represent an alpha particle, we can designate it by looking at the isotopic notation of helium with a positive 2 charge overall, which is written on the top right corner of the isotopic notation of helium. Another way that we can represent an alpha particle is going to be by writing the Greek symbol for alpha. And then on the left side of it, we're going to put on the top a number 4, which is the mass number, on the bottom a number 2, which is going to be the atomic number. Or lastly, the other way that we can illustrate it is by just writing that alpha symbol that it comes from Greek letters. An example of a radioactive isotope that is able to release an alpha particle will be uranium-235. The atomic number of uranium is 92. When uranium-235 releases that alpha particle, let me write the designation. So we write 4,2He2+. What we observe overall is that the new nucleus that it creates has the following characteristic. Since the alpha particle is going to have a number of protons of 2, we see that the number of protons in the new, more stable nucleus that is created is going to have an atomic number of 90. Since that alpha particle has a mass number of 4, then the mass of that new, more stable nucleus is going to be 231. And the identity of this new created nucleus is going to be thorium, which the symbol for thorium is TH. So understand that when these particles are released, you are going to be changing different aspects of your atom, and it will result in the formation of new nuclei, and in turn, that means new elements along with the particle that is released. The next type of nuclear radiation that you need to be familiar with is a beta particle. A beta particle, it is a high energy electron that it forms specifically when a neutron turns in an unstable nucleus into a proton. So the switch is that a neutron changes into a proton. Overall, because this beta particle that is emitted is going to be having a mass number of 0, and it has a mass that is less than a proton, we can designate this beta particle as the beta symbol for the Greek symbol for beta, Or we can have an E with a mass number of 0. That's why you see a 0 in the top left corner and then the -1, because that is the charge of the beta particle. An example of a radioactive nucleus that undergoes this transition and releases a beta particle will be the radioactive isotope for carbon, carbon-14. Remember that when it comes to the release of this beta particle, there's no change in the mass number. So that's why we observed that the mass number was retained as 14. But because the neutron changed into the proton, then the number of protons, which is going to change our atomic number, is going to be increased by 1. So when this radioactive nucleus, carbon-14, releases that beta particle, it actually forms the isotope nitrogen-14, because now, upon that release, we're going to have in that more stable nucleus 1 more proton, and it affects the atomic number. A third type of nuclear radiation that you need to be familiar with is a positron. This is similar to a beta particle, but it is produced by an unstable nucleus when specifically a proton is transformed into a neutron. Overall, understand that a positron has a mass number of 0, and the charge overall of a positron is going to be +1. So the symbol that we utilize for a positron, as you can see, is right here in the bottom of the slide, which is the letter E, where it has a 0 on the top left corner, a +1 in the bottom left corner. We can see overall, as it says in the first bullet point, that now a proton in our unstable radioactive isotope is going to turn into a neutron. So to give you guys an example of a radioactive isotope that is going to release a positron, here I'm going to utilize oxygen-15. So this is the isotopic notation of oxygen-15. We see that a positron is released, and in turn, there is no change to the mass number because that positron does not have a mass number. But because a proton is turned into a neutron, let's understand that our atomic number is going to be reduced by a value of 1. So this isotope is going to be now corresponding to a nucleus that has an atomic number of 7. So that means that what is created upon this oxygen-15 releasing this positron is nitrogen-15 as an isotope. So understand that the resulting atom is going to be the daughter nucleus. The last type of radiation that you need to be familiar with is gamma rays. Gamma rays, different from the first 3 that I introduced, does not release a particle. Gamma rays are high energy radiation rays that are released when unstable nucleus undergoes a rearrangement to generate a more stable nucleus. No particles are released. That's the signature of this type of radiation. So understand that these are emitted with other types of radiation. So it goes along with one of the ones that I just explained in the first 3 examples. Gamma rays also have no mass. And this is going to be similar to beta particles and positrons. And different from them, it actually has no charge. So that's why gamma rays, specifically, we see Give me a moment. So that's why we observe that when it comes to the symbol for gamma ray, we see the symbol gamma for the Greek letter that represents the gamma symbol. We see no mass number. We don't see a value for the atomic number. In table 2.4 from the textbook, which is on page 59, we can actually see the different types of emission. We can see their symbols followed by their charge.